What if space and time themselves aren't the foundation of reality, but just a side effect? What if everything our physics is built upon is actually secondary, ephemeral, like a shadow cast by something we don't yet understand? A new, bold, and truly mind-bending hypothesis at the intersection of quantum mechanics and gravity suggests that space and time might not exist on their own. They might emerge from quantum entanglement. At first glance, this may sound like a philosophical metaphor, but it's not. This is a scientific hypothesis backed by real equations, mathematical models, and, crucially, cutting-edge experiments and theoretical developments. Today, scientists openly say space and time are not fundamental. They might not exist at all until quantum connections between particles emerge. It sounds absurd, perhaps, but once the idea that the Earth revolves around the Sun sounded insane too. And yet, if this theory is true, it doesn't just explain a single phenomenon, it explains everything, from gravity to the emergence of time, the structure of space, and even reality itself. Imagine two dice, one thrown in Tokyo, the other in Paris, and every time, as if by magic, they land on the same number. What would you think? A trick? A glitch in the matrix? But it's not a trick, it's quantum entanglement, one of the wildest, most unsettling, and at the same time, most beautiful phenomena in nature. In essence, quantum entanglement is when two particles are so deeply linked that the state of one instantly affects the other, even if they are separated by millions of kilometers. Not through a signal, not through a wave, but as if outside time and space altogether. No wires, no antennas, no satellites. This is not speculation. It's an experimentally verified fact, recognized with the 2022 Nobel Prize in Physics. Alain Aspect and his colleagues ran experiments that closed all loopholes. Even when light from one particle couldn't possibly reach the other, the entangled connection remained. How is this possible? Honestly, no one fully understands. Einstein himself called it spooky action at a distance and tried for years to prove entanglement was a mistake. But nature didn't care. Experiment after experiment shattered his intuition like waves crashing on a rock. To visualize it, imagine a pair of perfect dancers separated by 1,000 kilometers. One makes a move, and the other instantly mirrors it. Not because they agreed beforehand, but because they're no longer two beings. They're one. And here's the key. This quantum link doesn't depend on distance and doesn't fade over time. It's not just a strong connection, it's a completely different kind of reality, where the boundaries between objects begin to dissolve. That's why physicists are seriously asking, what if entanglement itself is the foundation of space? What if we perceive distance only because the entanglement between objects is weak? And where it's strong, space loses meaning altogether? That would mean that the geometry of space, from gravitational curvature to the flow of time, might be nothing more than a byproduct of global quantum entanglement. And where there is no entanglement, there is no space. Our whole lives, we've been taught a simple picture. The universe is a giant stage, and matter and energy are the actors. Space is empty, time is a clock. Convenient, logical, but, as it turns out, completely wrong. This model works only until you look deeper, peek inside a black hole, or examine the early universe under a microscope, and the old theory begins to crack. Space and time start behaving not like a background, but as active participants in the drama. In fact, under certain conditions, they can vanish entirely, as if they never existed. Modern scientists like Juan Maldacena, Mark van Ramsdonk, and Ted Jacobson say, space and time are not the foundation of being. They emerge as a consequence of something more fundamental: quantum information and entanglement. We used to think the universe was a stage where quantum particles danced. Now it seems the stage itself is born from the dance, from those strange, invisible, yet real quantum links. Take, for example, the so-called holographic theory of gravity. It suggests three-dimensional space may be a projection of information encoded on a two-dimensional boundary. Our entire world, all its volume, may be just a shadow of a deeper, mathematically entangled structure, like the Matrix, but without the green code. Now imagine in this projection, everything depends on the density of quantum links. Where the connection between particles is strong, geometry emerges. Near and far, past and future appear. Where entanglement breaks, there's no distance, no time, only cold, terrifying void without coordinates. In other words, space and time aren't the scenery. They're a role, played according to a script written by quantum mechanics. Space can shrink, stretch, warp, and tear. But the most astonishing idea is this: it might be a secondary effect, like foam on the ocean surface or a dream triggered by a firing neuron. Only in this case, the neuron is a web of quantum states from which the fabric of reality hatches. Sometimes, a scientific idea shakes even the most stoic physicists. The ER equals EPR theory is one such idea. It breaks everything we thought we knew about the universe. Its core is simple, but the impact is like lightning on a clear day. What does it propose? That gravity and quantum entanglement are the same thing. Not similar, literally the same. Gravitational bridges in space-time, Einstein-Rosen tunnels or wormholes, are actually just entanglement between particles. But how can that be? In 1935, Einstein and Rosen introduced a mathematical description of wormholes, shortcuts between distant points in space. These became known as ER bridges, Einstein-Rosen. That same year, Einstein, Podolsky, and Rosen proposed the paradox of quantum entanglement, that once two particles interact, they remain linked, no matter the distance. This became the basis for the EPR paradox, Einstein, Podolsky, Rosen. For nearly a century, no one thought to connect these ideas until Juan Maldacena and Leonard Susskind suggested in 2013. What if ER and EPR are the same? What if the entire gravitational structure of space is nothing but a dense web of quantum connections? That's like saying the space between you and the stars exists only because the particles in this universe are entangled with one another. Where there's no entanglement, there's no space, no gravity, nothing. Yes, it sounds like madness, but this idea is gaining ground. Studies show the more entanglement between particles, the richer the resulting gravitational geometry, and vice versa. Sever the entanglement, and space breaks apart like shattered glass. This idea is radical because it makes gravity not a fundamental force, but a geometric effect of deep quantum interconnectedness, like a shadow from an object or an echo after thunder. Now think of black holes. They are, essentially, entanglement machines. And if wormholes are entangled states too, then black holes might be connected by quantum bridges outside time and space. Some physicists seriously consider the possibility that the interior of a black hole is a projection of information from the outside, stitched together through entanglement. If gravity is an effect of entanglement, then maybe the universe doesn't hold together because of mass and energy, but because of links between bits of information. The world isn't held together, it's woven. Try forgetting everything you've been told about reality. Whether it was from school books or science shows, it's all an outside perspective. The real magic begins on the inside, where nothing tangible exists, only connections. At first, it sounds absurd. How can nothing be everything? And yet, that's exactly how. If quantum entanglement truly underlies space and time, as recent theories claim, then the universe isn't a collection of points. It's a network with threads made of information. Atoms don't create space. Their connections create closeness. Interaction doesn't happen in distance. Distance arises from interaction. The geometry we know is simply a result of how strongly and with whom quantum objects are entangled. Picture a giant web, each node a quantum unit of information. These nodes aren't placed in space, they create space. Where the connections between them are dense, geometry forms. Where there are no connections, there is nothingness. This isn't just poetic. Scientists across fields are starting to see this not as metaphor, but as real physics. In quantum gravity, we now use network geometry, mathematical structures where the depth and shape of space emerge directly from the architecture of entanglement. A concrete example. In 2015, a team of physicists built a universe model using a quantum network and found that the more complex the entanglement network, the more realistic the 3D geometry it generated. It looked like an architecture of connection, where space isn't territory but logic. And this isn't abstract. It's supported by modern concepts like the holographic principle and AD-S-CFT correspondence, where the universe is described as a surface on which quantum states intertwine, and the inner volume is an emergent illusion. Mark van Raamsdonk, a leading voice behind this theory, said it plainly: by changing entanglement, we change the shape of space. Remove entanglement, and you destroy the fabric of existence. Now imagine the universe not as a sphere, not as space, not as a field, but as a living network where everything depends on relationships. You're not just a collection of particles. You are a node in an endless quantum web, connected to billions of others. And every action you take is a vibration on this web, capable of reshaping its structure. Theories are good, but in science, words are only as strong as the evidence behind them. And while the idea that space and time emerge from entanglement sounds compelling, experiments are starting to suggest it might actually be true. Experiment 1. Entanglement creates space. In 2022, a bold simulation was carried out in a Caltech lab. Scientists used Google's quantum computer to create a miniature artificial holographic universe. By entangling certain qubits in a specific way, they observed something resembling a wormhole inside the system. Not just fancy math, an actual simulation of ER equals EPR, complete with reproducible geometry. The topology literally emerged from the entanglement network. And if this can happen in a simulation, why not in our universe? Experiment 2. Destroy entanglement. Space disappears. Research in quantum field theory, such as Kitaev's work at the University of British Columbia, shows that reducing entanglement in a system leads to the collapse of geometry. Mathematically, it's terrifying. It's as if space literally disintegrates. When quantum objects become independent, disconnected, there is no more between them, and thus no more space. Like turning off Wi-Fi and watching the walls around you vanish. Experiment 3. cold atoms and artificial gravity. Experiments with ultra-cold atoms in optical lattices offer more pieces of the puzzle. In these setups, scientists create perfect light crystals, insert atoms, and precisely control their entanglement. And the results are fascinating. When entanglement changes, parameters analogous to gravitational fields also change. It's like manipulating artificial geometry. Of course, we don't yet have direct proof that space literally grows out of entanglement, but the clues are piling up. And if we keep going, we might one day pull the thread that unravels the entire mystery we call reality. What if your now isn't universal? What if before and after aren't objective markers, but just perceptions arising from the entangled quantum web? If space emerges from entanglement, logic suggests that time might be a side effect of its dynamics, not a fundamental dimension, but the result of changes in a quantum network. In truth, quantum physics has no strict arrow of time. Its equations are symmetrical. They work equally forward and backward. So where does our feeling of time come from? Physicists like Carlo Rovelli propose that time doesn't exist independently. It's just a way to describe change in an entangled system. As quantum elements interact, they evolve relative to one another, and in that mutual evolution, the sensation of time emerges. More precisely, time exists where there is information about differences. Near a black hole at the event horizon, time stretches and then stops. Fascinatingly, that's also where extreme changes in entanglement occur. Coincidence? Maybe, maybe not. In the holographic view, gravity and time within a volume are directly linked to the quantum system's behavior at the boundary. The stronger the entanglement, the more complex the internal flow of time. In other words, time slows down as the nature of quantum connections changes. An even wilder idea gaining traction among theorists. Time might not be global, it might be local. Different parts of the universe could have their own time, depending on their place in the entanglement web. Two unentangled objects might literally not share a common timeline. And if you could step outside this structure, you'd see that now isn't a single moment. It's smeared across the nodes of the system. Quantum experiments like the delayed choice experiment show that the result of a measurement can depend on something that happens in the future. This breaks our usual concept of time. But if it all depends on the structure of entanglement, then the future and past aren't a sequence. They're a static web of relations which we perceive as flow. In the end, instead of a familiar world where stars drift through space and time, we get something else entirely. Here, the actors create the stage, not the other way around. And the more connected they are, the richer, deeper, and more real the play becomes. Space, time, gravity, they may not be fundamental at all. They are emergent effects. I hope you enjoyed the video. Don't forget to leave a like and subscribe to the channel. I'll be sharing more stories about our mysterious universe.